students, welcome to another session of Spectroscopic lecture series. Now, as you already know, in the last lecture we have discussed about UV visible spectroscopy, and I have mentioned you there that the transitions which are responsible for UV visible spectroscopy occurs due to what? Due to electrons. So today we are not going to talk about the electrons, but we are going to talk about a very interesting new spectroscopic technique. You can see the topic here. It is Introduction to Ftir Spectroscopy. And you can see here in this first image, I have given the image of an Ftir instrument. And in the second image, the data which is provided to us by the Ftir instrument. Now, let's move on to the next slide. In this slide, I am telling you the region in which this infrared spectroscopy lies. But as you remember also, I have told you how to remember the order in which these different radiations, or rather these X-ray radiation or gamma radiation or ultraviolet or visible spectrum, or all these radiations lie in a particular order. And this order, how you can remember this order? I have told you already. The shortcut to remember is just remember the first letter of all these radiations. This is, for example, if we observe here gamma radiation, just remember this word GARI, X U V in my range. What? GARI XUV in my range. Okay? You have to remember the initials of these radiations initials. You have to remember GARI XUV in my range. Most of you know about the XUV 500. So you can remember it that way. GARI XUV in my range. This is what you will remember. Okay. Now, where this infrared spectroscopy lie? It's lie in the region of 0.75 micrometer to 300 micrometer. Further, it is comprising of three different regions. The number one region is near IR region, which ranges from, you can see here, 0.75 micrometer to 2.5 micrometer. And the next region to it is 2.5 micrometer to 15 micrometer. Okay, and the last one is extreme IR region up to 300 micrometer. Let me erase this. Now let's move on to our next slide. Now, why Fdir is called as Fourier transform spectroscopy? First of all, we should know what are the uses of Fourier transform infrared spectroscopic technique. Well, this technique provides us about the information of different types of functional group present in an unknown compound. For example, if we are using a solid sample and we don't know what kind of functional groups are present in it, whether there is an alcohol, there is an acid, or we don't know anything about it. So what we will do? We will put it in an Ftir instrument and it will give us some kind of data, it will give us some kind of information which will be about the different kinds of functional group present in it. Okay? And the next important thing, why the term Fourier transformed infrared spectroscopy? Well, it is this process requires a mathematical conversion. It requires a mathematical process. I will tell you when I will explain the section of its working. In that working section, I will explain why and where these transformations are required. Okay? Because when we finally need the actual data, so that data is required to be processed by a mathematical equation. Okay? Now let's move on to our next slide. Now let's start the actual concept from which we will know how this Ftir instrumentation starts working. Now what happens when the radiations falls through on a sample? This is a solid sample, just for the understanding. What I have done here, these are the radiations. Which radiations? IR radiations. What is happening here? These radiations are falling on a material. You can exemplify it like suppose it's a pellet, a small pellet. Okay. Now what will happen? The radiation will fall on this pellet. Now some of the radiations will be absorbed and some will be passing through. And that radiation which will be passing through is termed as transmitted radiation. Okay. And the radiation which is falling on the sample, we will call it exciting radiations. So there are two types of radiations here in this diagram. One is exciting radiation and the another one is transmitted radiation. Now take care of the fact that the intensity of this radiation which is getting transmitted is less. Why it's less? Because maximum amount or sum of amount is absorbed by this material. Okay. Now if the spectrum of transmitted radiation is observed, it is possible to obtain the information about the different functional groups. Okay. Now let's move on to the next slide. Now in this slide, I am going to tell you about the different vibrations which an infrared radiation can produce in a particular molecule. Now how can we understand this concept? How can we understand these diagrams? Okay, I'll help you to understand these diagrams. Consider this molecule as a water molecule. Okay, or rather consider me as a water molecule. See, my central body is like this atom here. Consider this portion as a ball, central ball, and two balls. Consider me like a ball and stick model. To my extreme hands are the two hydrogens of water. These are the two hydrogens. And consider my central body as the oxygen atom. Now, if I call it symmetric stretching, then what is the meaning of this word symmetric stretching? It means that if I am a water molecule, here my central portion is the oxygen atom and these two are hydrogen atoms. Now, what will happen? In case of symmetric stretching, a radiation will fall on this molecule and the bonds will either compress at the same time or they will stretch at the same time. So this will be the moment. This is called as what? Symmetric stretching. Now, when we need to understand the antisymmetric stretching, then what will happen? In case of antisymmetric stretching, one bond will compress and the other one will expand. So this is the moment. This is called as antisymmetric stretching. What about rocking? What kind of vibrations are produced in case of rocking? In case of rocking, the bonds will move like this. This is the moment. Okay. Now, the next one is wacking. What will happen in case of wacking? You know, this is towards you people. Okay. Or again, we can say out of the plane, like this or like this. These are the movements. Okay. Now, let's move on to the next type of vibration which are produced by the bonds. Here it's twisting. So one is towards you and the other bond will move backwards like this. This will be the movement. Okay. And the last one is scissoring. In case of scissoring, the bonds will vibrate like this. This is the movement. Okay. So I have told you different type of vibrations which are produced by these infrared radiations. You know, I have told you that whenever a sample absorbs infrared radiation, it will vibrate. And those vibrations are recorded by the Ftir instrument, which we further analyze. Okay, now let's move on to the next slide. Now this is a very important slide. Okay, observe it carefully. I am showing you the radiation spectrum of exciting versus transmitted radiation. Okay, now in the first diagram here, this one, it is showing the radiation spectrum of exciting radiation, and this one is showing transmitted radiation. But here you can see there is a fall in the intensity of the transmitted radiation. As I have told you in the earlier slide, what I have told you, that the radiation which is falling on the sample and the radiation which is coming out of the sample, it has got its energy decreased, its intensity decreased. That's why we got these falls in the Ftir spectrum. Now what happened when we got these falls? It means the molecules here have absorbed some energy, and when they absorb some energy, that's why there is a decrease in the intensity of these radiations. And due to decrease in the intensity of these radiations, there was a fall. Okay, and due to this fall we get the different spectroscopic graphs which are produced by the Ftir instrument. Okay, now let's move on to the next slide. Now this is the Ftir instrumentation. Now I will tell you how this instrument works and how the data is recorded. Now what happens here? First of all, as I have told you also in the earlier section, in the UV visible spectroscopy also, each and every spectroscopic technique is involving a use of a light source, and here we are also having a light source which is coherent light source, and after this source the light goes to the beam splitter. And what is this beam splitter? What is this beam splitter? It is a partially transparent mirror. Now what this mirror will do? Light will come here, some of the light will be passing through it. As it is partially transparent mirror, what it will do? It will reflect light into two equal portions, to two different mirrors. One is this one, M1, and the another one is this one, M2. This one is a movable mirror. Okay, this one is a movable mirror. This one is a movable mirror. What happens here? The light goes from this beam splitter to two different mirrors. Like this, it again reflects back from both the mirrors. Okay, it combines here. Okay, some of light passes through here, some goes down there to the sample. Okay, it passes through the sample, then goes to the detector, and finally we get the data which is provided by the interferogram. Now I have used the term interferogram. Let's understand why I am calling it as interferogram. See, because we got here two reflected beams which recombine here, and then these pass through the sample and the detector. What happened here? When these radiations came from these two mirrors, when these both were fixed, then their interferogram was a constructive interference when this mirror was fixed. But in actual analysis, what happens? We need to understand that we will move this mirror just to get the data. Okay, we will move this mirror, and what will happen when we will be moving this mirror? Then here we will get destructive interference. Okay, and we will get the interferograms. What we will get? We will get the interferograms. And to convert these interferograms, we need mathematical conversions. Okay, and those mathematical conversions are done by the Fourier transformations. That's why at the starting of this lecture I told you that why we call it Fourier transformed infrared spectroscopy. This is why, because we need these mathematical conversions to get the actual data. Okay, now let's erase all it and we'll move to the next slide. So this is how it was the working of Ftir instrument. Now we should know what are the types of samples which are analyzed with the help of these Fourier transformed infrared spectroscopic technique. Okay, we also need to understand these facts. See, all the type of samples, whether they are solid, they are powder, they are gas, or they are liquid, all type of samples can be studied with the help of Fourier transformed infrared spectroscopic techniques. Okay, now what happens in case of solids, for liquids and gases, they are placed in a cuvette in front of the detector. Light passes through it and then it goes to the detector, and then finally we get the data. And similar setup is also used for solids, but in case of solids and in some liquids, they are studied using attenuated total reflectance crystal. In the modern world, in the current world, this technique is generally used, preferably. What happens in this technique? You can see here, this is the crystal. The sample which is to be studied, it is placed on the crystal. Here, as you can see it here, the sample is placed here. Okay, what happens? Light from the source, this is the infrared radiation source. The light is passed from the this light source to the crystal, from polarizer to the crystal, and here you can see the light penetrates the sample to an extent, and then it is again reflected to the crystal. Again it is reflected to the sample, it penetrates to an extent, and then it again gets reflected. Okay, now what happens here? You can see it is getting reflected again and again and again. Now what happens with this process? More the number of reflectance we get more clarified data, we get more intense peaks. More the number of times it gets reflected, we get more intense peaks. Okay, now let's erase all this data. Let's move on to our next slide. Now this is the absorption band region. Now what happens in this region? You can see this graph. There are many types of peaks here. You can see some broad peaks, you can see some short peaks, you can see some intermediate in between region peaks. Okay, and you can also see, I have told you already that the region in which it lies is 7.5 micrometer through 300 micrometer. But in case of centimeter inverse, it ranges all the way from 400 to 4000 centimeter inverse. So this is the region where it lies. Okay. Now this graph gives you a lot of information. This is a very important graph where you can get relevant information, where you get about information about functional groups, where you get information about the fingerprint region. Let me tell you the terms which I am using, what kind of meaning they are having. See, I have divided this picture into two different regions. Okay, one is colored in this light blue color and the other one is represented in this color. Okay, here, this one. You know, this region which is ranging from 1500 centimeter inverse here, 1500 centimeter inverse to this region, this one, from here to all the way to 4000 centimeter inverse. Now this region is known as functional group region. Which region? This region is known as functional group region. Now what does this mean? This means that you will get the different functional group peaks in this region, which is ranging from 1500 to 400 centimeter inverse. And the next region here, which is from 400 to 1500 centimeter inverse, this is a fingerprint region. Which region is this? This region is fingerprint region. Now what do you mean by fingerprint? You know, this region, you will get peaks of the functional groups in these regions also as their impressions. Okay, for example, if any functional group is having a peak here, it will have a peak in this region also. So that will be double the conformation. You will be doubling the conformation. What kind of conformation? Yes, it is the same functional group which was present here, and it is giving its impressions again in the fingerprint region. Some people might confuse it. What do you mean by fingerprint? Okay, impressions. Fingerprint means what? Impression. The functional group which is present in this region, it is also giving its impression in this region. That's it. Next important thing is the peak intensity, peak type. See, peaks are of 2-3 types. First one, as you can see here, this peak. This is a very big and broad peak. Okay, this peak, you can say this is a broad peak, and this peak is tapering. Okay, this is a very sharp peak and tapering at the end, and also it is having like branches kind of ends at the end. Okay, and you can see peaks of this type also, which are medium in there, and you can also see such kind of small peaks. So these are the types of peaks which are observed in an Ftir spectrum. Okay. Now, as you will be aware of the regions in this graph, now you will be studying about the different areas. Okay. Now, first, let's move on to the next slide. Now, what are these? These are wave numbers of some common bonds. Now, let's make it more easier. Now, what will happen at these wave numbers? At these different wave numbers, for example, here it is OH 3650 to 3200. Okay, it is a very strong and broad peak. Now to get an idea of about this peak, we will go to the earlier slide. Observe this peak. This peak here. This is for OH group. Which group? OH group. Let's move on to the next slide. Now, as I have told you, the peak in the earlier slide was for OH group. OH group is which group? L. So, this peak of 3650 to 3200 centimeter inverse was for which group? This was for OH group. I hope you got my point, what I want to tell you. And this was a strong peak and it was a very broad peak, as you have seen in the Ftir graph. Now, look at the second one. This is the CH. CH bond gives its vibration in the region 3300 centimeter inverse to 2700 centimeter inverse. And see, its intensity is medium. Okay, now you can go back to the earlier data which was furnished by me in the previous slide. Now you can observe this region here. Okay, you can observe this region. Can you tell me, is there any CH peak here? Okay, just observe these markings. 2700. Where is 2700? Where is 3000 centimeter inverse? Okay, you just need to observe the data. Now let's move on to the next slide. Likewise, NH bond, C triple bond, N bond, C triple bond, C bond, C double bond, C bond, C double bond, N bond, and so on. All of these functional groups, all of these bonds, they will vibrate at a particular frequency. And when they vibrate, you will get a peak in the Ftir spectrum. Okay. Yes, their intensity, the intensity of their peaks, that may be different. For example, in case of white, it was a very broad peak. So likewise, you can remember this. Okay. See, there is no other way. You will have to remember the different areas where these gives their vibrational frequencies. You will have to remember these areas. You will have to remember these values. Okay. Then only you will be able to understand. Then only you will be able to identify which functional group is present in a particular organic compound. Okay. I have also told you the types of intensity, whether it's a strong, it's broad, it's medium, or it's different kind of categories. Okay. So whatever I have told you till now, it was about the different functional groups, their range, the intensity of peaks, how Ftir helps us to determine the different functional groups. So this was all about the Fourier transform infrared spectroscopy. You know, in this lecture, I have never told you that electrons migrate or they give the transitions. In here, what happened that that infrared radiation, what it did, it was absorbed by the atoms, or rather bonds, and bonds were vibrating. And why they were vibrating? Because they had absorbed some kind of energy, and due to that absorbed energy, the bonds were vibrating. And we measured that vibration, and we created with the help of Fourier transform instrumentation a graph, and from that graph we got the information and different type of peaks, I'll show you again. Like these peaks, we will get the peaks. When bonds will vibrate, we will get the peaks like these. Now you will be able to identify that this peak is for which functional group? OH. Okay, so you will be able to identify now how we can study a Ftir graph. So this was all about the Ftir, Fourier transform infrared spectroscopy.